Near-field communication. How does it work? NFC was designed for short-range communication between two devices for security purposes. NFC devices can be placed into two categories: passive devices, which can only send information, and active devices, which can send and receive information from other passive and active devices. An NFC chip contains three components: an antenna, a storage memory to store the information embedded within the chip, and a radio chip to detect the transmitting device's electromagnetic waves. Now we can ask ourselves, are NFC antennas actually antennas? The brief answer is no. NFC antennas aren't actually antennas, but rather inductors coupled back to back. Inductance is the property of an electric conductor to produce an EMF due to a change in the flow of current. The principle of operation that an NFC chip is based upon is known as inductive coupling. The inductor in this scenario is a coil of wire, otherwise known as a solenoid. Inductive coupling occurs when a time-varying magnetic field is generated by an active NFC device. When passed in close proximity to a passive NFC device, it induces a current within the receiving inductor. This in turn allows for the contactless transfer of energy. This is the same principle that is used for the wireless charging of smartphones and other devices. The principle of inductive coupling is based upon Faraday's law of electromagnetic induction, which states that the induced EMF is directly proportional to the rate of change of magnetic flux. The magnetic flux is given by the following formula, where B is the magnetic flux density in Teslas and A is the cross-sectional area in meters squared. The magnetic flux density of a solenoid is given by the following formula. From the formula we can see that the magnetic flux density is directly proportional to the number of turns in the solenoid and directly proportional to the enclosed current. Therefore, an increase in the number of turns or an increase in the enclosed current will cause an increase in the magnetic flux density and vice versa. From the magnetic flux formula, we can see that the magnetic flux is directly proportional to the magnetic flux density. Therefore, an increase in the magnetic flux density will result in an increase in the magnetic flux and vice versa. Therefore, relating the magnetic flux formula to Faraday's law of electromagnetic induction, we can see that an increase in the magnetic flux will result in an increase in the induced EMF. The magnetic field strength of a solenoid is given by the following formula. From this formula, we can see that there are two ways to increase the magnetic field strength. The first method would be to increase the number of turns, and the second would be to increase the current. According to Ohm's law, we can see that the voltage is directly proportional to the current, therefore increasing the voltage will increase the current. Such high currents are not suitable for devices such as cell phones, which limits the range of NFC to 10 centimeters. One last property we can talk about is the inductance of the solenoid, which is given by the following formula. According to the formula, when one is designing a solenoid for use as an NFC antenna, one must try to incorporate a large number of turns. One must try to make the radius of each turn as large as possible in order to increase the cross-sectional area, and one must try to make the length of the solenoid as small as possible in order to ensure the greatest possible inductance is generated. Thank you.